Hello, everyone. My name is Gert Lawler, and on behalf of the Foundation for Conservation of Atlantic Salmon, I would like to welcome you to today's webinar. If you wish to use translation, please navigate to the chat where you will find instructions on how to connect to the AI translation available, audio and/or subtitles. For today's webinar, we're very pleased to be hosting Dr. Corey Dawson. Dr. Dawson is an assistant professor in the landscape architecture program at Dalhousie's Agricultural Campus in Truro. Before moving to Nova Scotia, he earned his professional license in landscape architecture, OALA, certification in arboriculture, ISA, and completed a PhD in geography and environment at Western University, specializing in fluvial geomorphology. Corey also runs a landscape design build business, and his research work focuses on stream habitat and stormwater management planning. Corey's research aims to advance landscape architecture and river restoration design through nature-based solutions. GIS, 3D modeling, and hydraulic simulations are often leveraged to create digital riverscapes that enhance stakeholder engagement and support sustainable planning. Corey is particularly interested in developing new design frameworks to improve flood mitigation, ecosystems, and blue-green infrastructure. Today, he will be speaking on planning tools for targeting riparian and in-stream habitat conditions. After this afternoon's presentation, we'll be opening the floor for questions and answers. And now I will turn the webinar over to Corey. Welcome, Corey.
All right, thank you very much, Gert. Thank you everyone for coming. And I want to thank FCAS for funding this 2-year project. So we're able to do some cool things over the 2 years. We kind of started it with one project and we developed it into 2 parts. The funding also supported a grad student, Kai, to contribute to the work. We also teamed up with MyTax to get Anna Maria from Colombia, who helped out on the project last summer. And we've been working with the Maritime Aboriginal Peoples Council, MAPC, for a couple of years. They helped out with the project as well. And we're working together on some new things that I'm going to go over and touch on a bit today as well. Oh dear. Okay, there we go. So very brief introduction. I'm in the landscape architecture program at Dalhousie. So that's in the Truro campus. So I come from a design background, but it's a bit of a mixed bag. So I did my undergrad in environmental studies at Waterloo. I did my master's at the University of Guelph and did my PhD at Western with Dr. Peter Ashmore. So that was in geography. It was specializing in fluvial geomorphology. And that's really where I started focusing more on river restoration, river habitat analysis, and then trying to tie that into design as well. So for, I would say, over a decade now, I've been very interested in the idea of design simplification. So when I was doing my master's, so when I first started to look at this, where everything we design, almost everything in the landscape as humans, it's a simplification of the natural complexity of our natural landscapes. So roadways, developments, anything that humans use, they have to be leveled out. Geometrically, it's simpler. So I was looking at that, and then when I started my PhD, I found similar things were happening with how we restore rivers. So rivers are really very dynamic systems. So they go through erosion, deposition, process form relationships. But when we get too much erosion, for example, that starts encroaching on our infrastructure, we come in and restore it, but often what results is kind of this geometric simplification. So just kind of show an example. This is Highland Creek in Toronto. Top image is what it was prior. It started migrating towards the infrastructure, and they came in to restore the site. And what we often see is more symmetrical, broad meanders. We have pool riffle sequences that are kind of evenly spaced out. Usually the channel will be widened to reduce flow velocity. So there tends to be this overall, whenever we're designing nature, we're kind of simplifying it. It's really difficult to really get the full complexity of natural processes. So a lot of my kind of research rooted from that idea ties in kind of indirectly and directly across different projects. Today, I wanted to essentially present three different areas, kind of three different projects that we're all looking at rivers that feed into the Cobequid Bay. The first part, we'll be looking at impacts of Hurricane Fiona, looking at canopy loss resulting from that, and also some stream bank morphology responses. Next part is targeting resilient canopy clusters. So we're using the data to look at, through time, what kind of canopy patches showed some climate resilience or were able to adapt or less vulnerable to these types of storms that can help guide planting design. And the third part is mapping in-stream habitat. So this one's a bit new. This is kind of what we're working on right now. We're tinkering with some other planning tools. So this one, we're looking more specifically in one of the rivers. On in-stream, we're using an egg incubation project that MAPSI was working on to kind of lay this out. Overall, what I'm going to try and do in this presentation is go through a bunch of what I think are very interesting and applicable tools that can be used for analysis, planning restoration projects, mapping things, and also help with design. So these are the sites that we've been working with. They are within 4 watersheds. So we have the Portapeck, Great Village, Folly, and DeBert watersheds. In 2024, we took a drone, we collected LiDAR along the main channel from the mouth, working our way up. So Dalhousie did Portapeck and Great Village. MAPSI collected data for Folly and DeBert. And with this new data, we have imagery. So at the top right here, we have digital surface models, or DSM. So this has the canopy as well as the topography. And then we also have DTMs, digital terrain models, or digital elevation models, where we have just the topographic representation. So with this research, we're looking at comparing changes through time. So with the provincial LiDAR data, we have data sets for all 4 of these rivers from 2013 and 2019. And then we're comparing that with the new data we collected for 2024. So first part of this, looking at impacts of Hurricane Fiona. So we first looked at canopy loss. We're really interested in comparing data from 2019 and 2024 because that gave us a representation of before and after Fiona, which occurred in 2022. So the first step in this kind of workflow, we created these canopy cover polygons, which you then compare, statistically analyze. The next step was looking at morphology responses. So in this step, essentially we took one DEM, so the older DEM, we subtracted from the newer DEM, and that gave us maps showing where erosion or deposition had occurred, so elevation changes. So in the small kind of diagram here, you can see 2019 and then 2024, and we can map out where scour occurred based on subtracting these DEMs from each other. So that's kind of referenced as the DOD approach. And then we finally looked at some hydrometric data just to get an idea of what the hydrology was doing throughout that 11-year time span from 2013 to 2024. So looking at the canopy cover loss, we first kind of broke this down yearly. Essentially, what we found was growth from 2013 to 19, followed by decline from 2019 to 2024. We also split this up into mature, medium, and low canopy. And what we were really interested in here was this double-digit decline in canopy cover between 19 and 2024. So this is an indication of canopy loss at this point, likely resulting from Hurricane Fiona in 2022. So with our imagery, we can look at different areas that took larger impacts. We could also map out clusters of where we lost that canopy to try and narrow down some of the effects from the storm-induced wind throw. So when we went to the field, we were able to ground truth some of this. A lot of down trees. We didn't do a full inventory. It was hard to kind of identify trees 2 years later, but it seemed a lot of it, most of it was coniferous, likely balsam fir and spruce that took the brunt of it. There were some deciduous. We saw a lot of birch that were kind of uprooted. And we saw a lot of these uprooted kind of forms here. So this is Anna Maria, just to give a reference scale. So there was a lot of damage from the sites that we kind of visited in the field that supported some of the analysis we did on canopy loss. Then we looked at morphology change. So we did that DOD approach to map out scour and aggradation. We saw some things that we're expecting. So up here in this figure in 2013, you can see riparian canopy on both sides of the channel. In 2019, we start to lose some of that canopy, and we have this erosional form starting to develop. We lose more of the canopy. There's more scour erosion, and the channel starts to widen. So kind of fundamentally, when we lose that stability, that's what we're expecting to see. Also along near the mouth or estuary of these channels, this is where the most erosion occurred, where there's little to no actual canopy cover. So the channels are a lot more active down at these areas. So we're able to map kind of increases and decreases in elevation change. But whenever you're comparing different data sources, things like in the right-hand corner up here, the drone may pick up things like dense leaf litter, like that were deposited as actual aggradation. And likewise, the drone can't quite get under undercut banks. So it's not picking up that kind of erosion. So there might be more or less erosion than we were able to quantify, more or less erosion or deposition. But we were able to get some general kind of estimates of how this changed. So what we're found quite interesting across all 4 watersheds, or where we had data on the river channels, between 2019 and 2024, we saw a decrease in scour, but proportionally, we saw quite a significant increase in aggradation. So there was more aggradation occurring along the stream banks following Hurricane Fiona than were prior. So on this kind of bar graph down here, you can kind of see, especially in case 1, there was virtually kind of no deposition or aggradation occurring. And these all spike kind of following that next data set. Then we looked at historical flow. So we're interested in seeing, was flow contributing to what we were finding? Based on the data at the time of the hurricane, we did have kind of a peak flow, but relative to that whole 11 years, it wasn't anything too drastic. So just based on that kind of simple reference, we kind of made this conclusion that riparian canopy cover decline was driven by wind throw, so it wasn't driven by heavy rainfall or flooding events directly. And the aggradation that we found along the stream banks was likely resulting from widespread canopy loss at the watershed scale. So all the destabilization of the soil at the watershed scale extent loosening the soil. Eventually, all that sedimentation is making its way to the channel. So it's a much broader kind of process response sediment regime change than simply along the channels or riparian area. So with all that loss, we were thinking of how can we target some areas that remain resilient or that were less vulnerable to that type of wind throw. When we were conceptualizing this, we were thinking about how to look at canopy cover. And this is used in design. So we want to reduce wind. So if we're thinking about landscape design, offering some refuge for your design space, having a diversity or variety in tree height or canopy height, different plant types, diffuses the wind. So it lowers the wind velocity, it insulates areas. But from an ecological perspective, it also breaks up those really high intensity winds. So it's an actual protective mechanism to have diversity in canopy height for the actual stand that is existing in a forested area. So to track that, we applied this focal variety statistic, which is conceptually very simple to use, but it is dimensionless, it's really flexible, and it is scalable. So this can be applied to any raster-based data set. So it could be your digital elevation models, it can be applied to canopy, it could be applied to imagery as well. Anything that has pixels, this tool can essentially be used for if you're interested in looking at variety or diversity in values. So in this diagram here, this is using a window, and a window is just a set parameter. It scans the entire surface or raster surface, and it'll give you values based on that input. So this window is a 3x3 rectangle window. So this has 9 cells within it. And when you run the variety metric, all it's doing is saying how many different values are in each of those windows. So if all the values are the same, it'll give you a variety value of 1. So there's no variety. If all the values are different, it would give you a value of 9, meaning all 9 cells are different. And this little diagram here gives you a value of 7 because there's 7 different kind of values within those cells. When you're using this tool, you can also adjust the shape of it. So you can increase the size with rectangular. You can have a circular window. Different parameters can do different things. So there's a lot of flexibility based on what type of analysis you want to do and scale. We did receive, actually on Monday, some reviewer feedback on a paper we submitted. One of the reviewers asked, is there an open source or free kind of approach to do this, which we hadn't thought of before. But yesterday I did a bit of digging, and QGIS, which is free, it's open source. They do have a toolbox, grass toolbox, and the operation is called diversity. It does the same thing. So it'll give you a diversity, which is the same as a variety. It'll tell you basically the variety or diversity of those pixels within the moving window. Just if you're interested, it's also available through that way in QGIS. So I've been using variety for other approaches throughout the years. When I was doing my PhD work, we developed this geomorphic form variation approach. So it's GFV. We applied this in the channel to look at morphology changes on the riverbed. So for this metric, we used input raster. So we had a digital elevation model. Then we ran flow direction, aspect, and plane form curvature as our input rasters. And then we applied the variety statistic to those. Once we have those variety statistics, we can then apply a hotspot analysis. And all this does is target clusters where those variety values are statistically significant. So it's narrowing down to the most important areas based on those parameters we applied. So the first thing we did, we used a flume experiment through time. So down here we have kind of this cluster forming. Then we have this bar forming within the pool. The cluster starts to migrate. The bar starts to become larger. And what we found was that statistically significant clusters seem to start developing along the downstream margins of these bar forms in this first trial. We then used it with River Builder. So if you've never used River Builder, this is another great tool. There's a link to the manual. It was developed by Greg Pasternak and Rocco Brown. And what this tool does, it creates synthetic 3D river channels that are based in fundamentals in fluvial geomorphology. So it's actually creating a digital elevation model based on specific inputs. So this was really helpful because we started at the top right here, just a straight channel. We implemented in some width diversity or variation in width, then started putting in meanders, increasing the frequency, amplitude of those meanders, until eventually at the bottom we get these more irregular shapes that are more representative of natural channels. So this tool is really useful because it was a really controlled environment where we can do some further testing on our GFV that we developed and map those things out. And in the final stage, we applied this to real-world restoration projects. So we were looking at before restoration and after restoration, mapping out these clusters and seeing how, in this example, this is Wilkett Creek. You know, we get clustering, high diversity or variety with the proposed and implemented design. That diversity starts to disperse. So we have this kind of statistical simplification that we could also map with this approach. And with that research, we found all stabilization projects. So anything that wanted to stabilize channels did decrease the overall complexity, but more rural projects that were specifically focused on enhancing in-stream habitat were actually increasing habitat and geomorphic complexity, which kind of an interesting finding there. But that was just a bit of context to set up. We're going back now to this project where we're applying that variety tool to riparian canopy now. So the idea was to look at riparian canopy with our data sets from 2013 and then 2024, apply that hotspot analysis. So we're getting clusters of those 2 years. With those clusters, we then essentially clip them, and then whatever's remaining is an indication of high canopy variety that remained significant for that 11-year time span from 2013 to 2024. So we trialed out some parameters in here, adjusting like the size and shape of the variety input. So this diagram just shows we use a circle with a radius of 3 meters, 5 meters, 10 meters. These will give you different values, but it also supports its kind of flexibility. So if you're looking at a full watershed, you want to get a gauge on canopy cover at that scale. Likely you're going to want to increase the window size. But what we were particularly interested in here was the sensitivity of these different inputs, because we wanted to look at how sensitive these inputs were to try and get the most accurate representation of canopy cover change and resiliency. And what we found was a circle shape with a radius of 3 was the most sensitive. So that's how we calibrated the variety input. Then we tested hotspot inputs. Really what we're looking for here, there's a lot of numbers, but we wanted to target kind of the most precise area. So we wanted a low surface area that we can target the most accurate or smallest clusters that we could actually do field work on. So just an example here, this kind of goes through the process, but this fixed distance band. This was a good cluster that showed high variety when we ran the tool, but it was also picking up this single tree here as a cluster point. So that was interesting because it's actually picking up variety within a single tree, but we were interested in narrowing down to the cluster of tree composition. So basically with this testing, we wanted to get down to this type of cluster here, this inverse distance squared. We're showing us a cluster, but we're not getting that external kind of individual input from single trees. So that helped calibrate both of our variety and hotspot kind of input parameters. That produced a target map. So kind of envision a map with a bunch of clusters on it. That helped guide where we then did field work. So we went out into the field across those 4 rivers. We did tree inventories. So we collected tree inventories, did tree IDs, did diameter breast height. We then applied additional measures. So the Simpson's Diversity Index, looking at the diversity of trees that we identified. We also applied the NDVI. So this is a greenness, canopy greenness index that we applied to the imagery. It's really looking at canopy health as another indicator. We looked at slope aspect for each site, and the idea here was to layer different indices to find the best performing sites that could essentially guide a riparian planting design. So going through the whole process of mapping out statistically significant variety clusters, doing the analysis in the field, applying additional metrics to narrow down what tree species compositions are likely to remain more resilient or adaptable to future storms that we can implement into a design. So we went out and found 20 sites that met this criteria. We did our tree inventories, took our diameter breast height. Within each of those sites, we were able to track, the surface area of that cluster, the average slope of the site, aspect, number of trees, and number of species, which gave us valuable information to kind of support our initial variety mapping. Then we looked at the diversity of species. So we're interested in seeing, is that canopy height variety just, the same species at different growth stages, or are we having high diversity of different species within these sites? And generally what we found, really we had 1 or 2 outliers. So P1 here, it was really dominated by balsam fir. But largely for the other sites, we did have this diversity of tree species, which we were expecting and we were kind of hoping for to kind of support a more adaptive planting design. So this bar graph is showing the composition of all the tree species. Up here on the right, we're looking at mean height and DBH, so looking at relative maturity of each of those clusters. And then on the bottom right here, we're comparing our diversity index with that NDVI. So we're looking at species richness versus greenness. We applied those metrics to see what are the best performing sites out of that whole data set that could help with a more wind throw resilient approach to design. So we found that G3 and G7, these were both in Great Village. And what we did here was propose that we can use these species compositions as a palette for design. So similar, like if you're painting and you have a palette of colors, based on all that analysis, we can say these species seem to work well together, at least are less vulnerable to wind throw based on all that analysis. So with this palette, this is where kind of the design decision-making comes in. We proposed this kind of conceptual riparian design. We found a site with a similar slope We wanted to implement some cold water refuge to increase salmon habitat along the riparian area, also provide stability. So we wanted more deep-rooted species in this composition rather than shallow-rooted species, for example. We kind of took that palette, proposed this design, wanted to be increased diversity, stability, while also offering in-channel habitat. To kind of just illustrate the workflow from mapping out variety, doing the field analysis, bringing that back through to the actual design decision-making phase. So that is our new tool. We're going to submit, hopefully we'll get that paper published on that specific tool soon. Now I'm just gonna somewhat switch gears, but it does tie back into almost everything I've been saying here with some new things that we've been working on at the in-stream habitat extent. So we've been working with MAPC. We jointly purchased bathymetric LiDAR from NSCC of the Folly River. So this is really great data. It goes from the mouth of the river all the way up past the natural barriers. It also has some tributaries that were mapped here. And the bathymetric data gives us actually the riverbed topography, which we didn't have prior. So this opens up a lot more opportunities to do some kind of interesting things within the riverbed as far as habitat mapping. So this gives us the riverbed topography as well as the canopy. These are both 0.5 meter resolution, and then our imagery from this survey is 5 centimeters. So we get really high resolution imagery as well that we can work with. So we were trying to think of, what kind of things we can test out and how we can calibrate some new approaches to use. And we thought that MAPC has been kind of taking a lot of field data from the Folly River. A couple of years ago now, in 2022 and 23, they completed an egg incubation project in the Folly River, and they're also continuing on a 4-year project titled Restoration Through Overhead Refugia Exploration. I believe I got that right. Their Restore project. So they're continually collecting data, which is really valuable for calibrating kind of new tools. So what we did with this kind of new, smaller project is that we looked at the egg incubation project. And in November 2022, essentially they put out the baskets. They had a 15% survival rate, and it withstood kind of a relatively high peak flow. We got this value from the Great Village River, which has the gauge, just as a reference. To increase the survival rate, they then placed it around 5 meters upstream. They placed the baskets 5 meters upstream. In November, they came back shortly after, and the baskets were all washed out. Some never to be seen again, from my understanding. But the actual peak flow in that time was less than the year prior. So the basket placements were really close in proximity, but clearly there were some substantial differences in the hydraulic geomorphic conditions within those two areas. So we used that to kind of set up our question, and we thought, how can these findings support new mapping applications for identifying new suitable egg incubation basket placement sites as far as planning. So what we did, we looked at where the baskets were placed. We extracted upstream and downstream from the site. So in this little image here, you can see 2022. So this was the stable basket placement. 2023 was a destabilized or washed out basket area. We wanted to compare what the conditions were, largely on what the conditions were that the baskets remained stable, And we wanted to model high flow and low flow to see how we can map those things. So MAPC collected throughout the years wetted extents or wetted widths throughout the Folly River, and we used that to calibrate some high flow and low flow simulations. So we used FCAS to model some outputs. So with FCAS, we modeled a flow velocity layer. We modeled a water depth layer. We then brought in our GFV, so that was that geomorphic form variation approach, so variety of the riverbed. Then we also added a canopy cover layer to add that cold water refuge layering as well. So on the far left here, this was our high flow velocity layer output. So this was calibrated based on the highest wetted width that MAPC tracked in the field. We then did low flow water depth. So this was the lowest flow. This was last year when we had that drought to kind of see what the lowest flow that we can calibrate from field data was. And what we were targeting here was criteria where that stable basket placement aligned with how we can layer these things. So we extracted the data from that EB1 is what I'll call the stable egg incubation location. So we extracted everything at and below the flow velocity of 0.7. So that was our maximum flow velocity that we wanted to look at. Then our minimum depth was 0.18 meters. So this, everything higher than 0.18 meters, we wanted to extract that and layer it onto our flow velocity layer. We then ran the GFV, and with the hotspot analysis, we found that 95% category as far as mapping is where our EB1, that stable site, produced. So we wanted to look at areas in the river that aligned with that. And then we added in riparian canopy cover as a fourth kind of layering approach to this process. So we had these 3 layers, and what we did was essentially overlapped all of these, extracted each of these layers to get one map where all of those criteria were met. So where all 4 of the inputs overlapped, that gave us a map to kind of target sites that may be suitable or stable for future egg incubation planning. So that was built into a bit of a larger workflow. These are the 4 kind of layers that were just referenced. That gave us an in-stream target map or target sites. We then did a bit more mapping. We applied the geomorphic unit tool to get geomorphic units in the channel. Another great tool, the geomorphic unit tool, this was developed by Joe Wheaton. And what this does is a semi-automated tool that will map out based on different inputs. So you have a digital elevation model, you do bank full, low water level, thaw wag, and center lines, and we'll map out things like pools, riffles, bars within the channel. So to get accurate representations, you do have to ground truth it with field data. But we were interested in using this as kind of a mapping approach to see where these sites align as far as potential for natural red conditions. Another thing we looked at was potential connectivity. So all we did here was we took that low flow water depth layer and we just measured on really low flow, what's the surface area of that water pocket essentially of where those sites were located to see relatively how the connectivity was aligning with those different sites that were mapped. So with those 2 additional kind of measures, that reduced our overall target sites down to ones that were more suitable or more mimicking natural red conditions for incubation basket placements in the future. And the final stage here is we ran a morphodynamic model to stress test these. So what we did was, it's a sediment transport model, and we wanted to see, are these sites likely to remain stable, looking at the existing and modeled topography. So are we going to get erosion or scouring where we place these baskets? Are we going to have smothering or aggradation? Just as a stress test and final measure to kind of map out the potential for the stability of these sites. Okay, I'm running out of time. Okay, so we ended up having 23 sites that met those 4 criteria. Everything below that 0.7 in velocity, above 0.18 in water depth. And all of these also corresponded with areas that had canopy overhang. We also have the GU, so these are geomorphic units that corresponded with these. We found kind of some interesting things looking at the data. So for example, S4 and S5 here, these were really deep pools compared to the rest of the data. These were situated just upstream from a bank projection here. Another kind of interesting thing was that there were 9 additional sites that were in pretty close proximity to the original incubation placement of those baskets. So ideally, what we wanted were sites that were on riffle, like labeled as riffles. They're at the tail end of pools, so kind of at a transitional area upstream or downstream, I should say, from pool forms. So with that geomorphic unit tool, we didn't have any riffles. In the far right here, we did have riffles throughout the channel. Some were pretty close, but none were mapped directly on riffle features. But we did have a few that were on forms that are at the tail end of pools. We found 4 of those sites. Right here, these are the gut maps. So these are showing the geomorphic units, showing the configuration of those, and we were able to identify these 4 sites were at the tail end of pool features that were mapped based on that tool. The second column here was our relative connectivity. So we're looking at the surface area of water depth based on very low water simulations. So for example, R2 here had an area of wetted extent of 694. And comparing that to R4 at the bottom, this was kind of a isolated patch that only had a wetted extent of 5 meters squared. So there's quite a bit of difference between these. This helped us just narrow down in the decision-making process of where we want to put these new incubation baskets in the future. And on the right here, this is the results of our morphodynamic model. So the black line is the existing riverbed and where the sites were located as far as red conditions or basket placements. And the red line is the simulated surface. So this is how it adjusted based on the sediment inputs. So R1, for example, we have some scour, some erosion at the basket placement area. R2 was quite stable. There was a lot of movement or morphology change kind of upstream, but the actual placement target area we had was quite stable. R4 and R3 both showed that there was likely to have some aggradation occurring or deposition in the future with some high flows. So based on all that analysis, we found that R2 was the best performing site. And kind of funny, I guess, R2 was about 12 meters downstream from the original incubation site. But we could with confidence say we looked upstream and downstream of the channel. We looked at many different metrics, simulations, and with some confidence we can say if we move the baskets around 12 meters downstream, we might be able to get a higher survival rate. So just touching on potential future research, what we would like to do and are kind of working towards is actually installing a riparian planting design using that canopy variety hotspot approach. That would be nice for long-term testing, especially like 3, 5, 10 years from now. Does that composition of plant species that we mapped out actually withstand high wind throw? Another thing that would be interesting is using the geomorphic unit tool to map in-stream habitat before and after our morphology models. So how do these simulations change the configuration of those geomorphic units? Also, running River Builder, we're looking into how we can design side channels within potentially the Folly River so that we can simulate different scenarios and how those can kind of be implemented into the real world kind of digital surface as a planning approach. And one thing we haven't done, we'd also like to do is apply the GFV to hydraulic rasters. So we looked at riverbed topography. Now we've looked at canopy variety, but it would be interesting to link that with hydraulic rasters. So flow velocity and water depth and things like that. And as of yesterday, now I'm thinking it would be interesting to see how the ArcGIS Pro variety matches against the QGIS diversity, how those line up. But yes, those are just some ideas we're working with. So thank you very much for listening. And my contact, if you have any further questions, at the bottom here, and I can answer any questions.
Thank you so much, Corey. That was an excellent presentation. We'll now open the floor to questions. Please raise the little hand on your screen and I'll be able to unmute you if you'd like to ask a question. The other option is if this doesn't work or you'd prefer to just type in your question, I will read it out loud for you. I'll put this out for questions. We'll just give this another minute to see if anybody has questions.
Sounds good.
Okay. Okay, I have a written question here, Corey.
All right.
Was the Bathy LiDAR collected by way of plane or drone? And is Bathy LiDAR required for GUT, G-U-T?
Yes, so the geomatics team at NSCC collected that by plane, and then MAPC and DAL purchased it. In order to run the GUT, you do need the riverbed, so that could be done by total station, so going out and kind of collecting the data that way. It's a bit more time consuming and you'll never get like as high quality as the bathymetric LiDAR collection. But to run the GUT, you will need kind of the riverbed kind of track those, because it is realistically it's trying to map out the riverbed for that to apply the GUT.
Okay. Is there anybody else that would like to ask a question?
Yeah, and if anyone knows I have been looking into trying to get like the correct laser to collect bathymetric data with the drone we have, and I was getting quotes in the 150 to almost 300,000 just for the laser, which is insane. So yeah, hoping those prices come down, but ideally collecting with drone would be the best strategy.
Okay. That was Kaylin Murray that asked that question, and they've replied, thank you for your answer. It seems that that's the end of the questions so far. If you have more questions later, please feel free to reach out to Dr. Dawson directly using the email that's on your screen right now, or you can contact us at the foundation and we will certainly pass it along. We've recorded this session and it will be available on our YouTube page. This concludes our webinar series for 2025-26. We'll be starting up again in the fall with a whole new slate of topics. If you have suggestions for future topics and or presenters, please contact us here at FCAS. We would really like to have your input. So a big thank you again to Corey and to everyone who participated. See you next time, everyone. Bye now.
Thank you. All right.
You're still there?
All right. Yeah.
Yeah. I'm going to leave and we can come back on.
Yeah.